Hi, good morning everybody. Thank you for the promotion. I'm actually doctor, not professor, but I'm going to tell you about our concept for a recoverable microsatellite. We like this satellite so much that we intend to bring it back. So I'm Sean Tuttle. The team members are the students Kieran Davis, who did the communication subsystem, Scott Johnson, who looked at the power subsystem, and Mitchell Woodward, who looked at the re-entry aspects in the thermal protection system, and Andrew Neely, who supervised the re-entry and thermal aspects. So I'm not going to say too much about the mission or explain why we want to do microgravity research, but the idea that was put to us to develop was to provide regular access to conditions of microgravity for long duration experiments. And this was largely motivated by the fact that it takes a very long time to get your experiment onto the ISS. The other key important thing is the requirement was to bring the experiment back after it had been completed. And while this is possible with the ISS, it's not easy, and it costs a lot more. The other thing is it's for long duration research, so things that you can't do in a short time in a drop tower or a parabolic flight. And of course the field is very wide of the things that one could do in microgravity, and we learn all the time about new things that lend themselves to that. So one important thing that I'm going to say is we're trying to balance flexibility of the mission with simplicity. Now clearly doing this kind of mission is quite challenging, it's complicated, and there are going to be some big cost drivers. So on the one hand, to try and make it commercially feasible, we want to be as flexible as possible, and that is allow any kind of experiment to fly on board, no matter what sort of data it produces and what its requirements are. And similarly, to be able to fly in as many different orbits as possible, and that will allow us to fly with as many co-passengers as possible, and that helps us become more competitive. This we have to balance against simplicity. Ideally, we would just design for a single payload that we know everything about, and a single scenario for which we can define their subsystems quite clearly. But that would then make us with a very limited MERS. So we need to balance these two things, and our approach has been to come up with this idea of a MERS experiment package. And basically what this is, the satellite will have one CubeSat sized payload compartments, which will then have very standard interfaces and will be uniform. The other thing is we've considered as wide a range of possible experiments as possible. So that means in terms of what measurements they might want, how frequently their data would be sampled. So we've come up with a suite of options for which we can accommodate the maximum data output, whether we have one experiment that spews out data at kilohertz for a day, or we have one that only requires 2 measurements per day for a month, and maybe wants video data as well. So combining all that then allows us to get started with the design and the sizing to look at the feasibility. The other important thing is, although we're not a CubeSat, as you'll see shortly, we're going to make as much use as possible of off-the-shelf CubeSat type equipment. And then we're given some flexibility, but we've also limited exactly the orbital ranges. So we're focusing on this kind of altitude, 400 to 500 kilometers, and the range of inclinations there, probably well below 47 degrees, but up to polar. The concept of operations is quite straightforward, really. We launch, and then we spend a period of about 2 months, and that's the total life of the mission. And during these 2 months, we will conduct the microgravity experiments in an inertially fixed orientation. And during that time, we download the data either during the experiments, but certainly in between experiments. So the experiments will be conducted sequentially, and we'll come to why in a moment. on completion of all that, and once all the data has been downloaded, and that's important because we don't know what might happen in re-entry, of course, hopefully nothing bad, but it's important to get all the data down first. Then we will start our deorbit phase, which we will do by deploying some sort of drag enhancing device to a sort of medium extent. We'll fly down slowly to around about the 100-kilometer altitude mark, and then during this phase we will use drag steering. Once we get to that altitude, we will conduct several orbits during which we really characterize our orbital parameters really well, so that we can then predict our re-entry as accurately as possible, and we fine-tune the attitude with the reaction wheels. And then follows the final sudden large increase in drag area for the actual initiation of the deorbit, and then we jettison that drag device plus the UHF antennas and re-enter. Oops. Now, I'll show you the satellite. As you can see, doesn't look like a traditional CubeSat. This is a model of it here. So basically it's a re-entry vehicle which has to function as a low Earth orbit satellite for about 2 months. On the front heat shield side, we will have an integrated solar array, and on the rear side we will have the main radiator for thermal reasons. Here you see the two flight configurations, the experiment mode where we're inertially fixed and we have sun on the solar rays, radiator at the back. Then for the re-entry phase, we will go into this more stable configuration, but also not so good for power and so on. The satellite itself, you can see a cutaway here. The front has the solar cells embedded in the heat shield, which goes all the way around. It will be an ablative type material. Inside we have the payload modules and all the other equipment. And the internal structure is a double kind of structure, which relies on the same sort of effects that the woodpecker has in its head for protecting its brain. So that provides a lot of shock isolation and also some thermal isolation. This is our main radiator. And here you can see the temperature predictions through the heat shield material at the worst case of heating during re-entry. And the temperature rise at the back of the heat shield in the worst case is about 50 degrees. In this current configuration we can produce about 38 watts, and in the worst case about 10 megabits per day we can download with a comfortable link margin. The onboard temperatures are okay, and the mass currently is around about the 27 kilogram mark. An important thing is we don't have to deploy much other than the antennas and the deorbit device, and the baseline is to have no parachute, which that means a hard landing, but it's more reliable in that we don't have to rely on something as critical as that. The key performance parameters, level of microgravity is more or less guaranteed by the orbital height, but we can do things to improve it by our flight attitude and how we locate the equipment inside. The temperature stability, that will depend on the nature of the exact experiments flown each time. The attitude stability is very important prior to re-entry, and in particular knowing what it is. Obviously during re-entry, thermally and mechanically, we don't want to damage the experimental results. And finally, the payload data must be brought down completely before starting re-entry. The next slide just shows basically we can make the system work in our range of orbit extremes. 47 degrees is simply because we looked at making it work with one ground station based in Canberra. 98 degrees because that's a very popular orbit. Obviously the more ground stations we can include in our network, the better, and the less delay between experiments. Power is the reverse. 47 degrees is worse because of the beta angle, but as you can see, even assuming very frequent reaction wheel use and with a downlink every time we have visibility, the power generated is higher than the power consumed. We're looking at how the shape and size of the body influences the power generation. And importantly, we're looking at the whole re-entry. Depending on the angle at which you re-enter, you get a different peak heating rate. This then also drives other parameters, the time of re-entry, the maximum deceleration, and so on. And then we balance those to see where do we get about the best mix of all of those. And that occurs at around about 30 degrees re-entry angle. And then in turn we look at the nose radius and the body dimensions for power generation and peak heating. So I'll just go on to some last things. We see this both as a good chance to make friends. So one of the important things behind MERS is collaboration, and at the moment we've got just started heat shield development with JAXA. We've had a number of good conversations about joining ground stations into a network with people in Ghana, Canada, Germany, Italy, offers of software from a company in Switzerland. And so this has been a good thing about the whole MERS project. Business-wise, it's clearly difficult to make it attractive at the moment while the ISS is there. Later that will change. An important thing to consider is the economy of scale. Maybe the MERS we're looking at is not the right size. We need to fit more payload modules in there. But we do have, even within the 50 kilogram limit, we've got quite a lot of scope to make our current spacecraft bigger. Yeah, so at the moment we've got this program. I've just got some funding to do tests at JAXA and with support from KIT. We've commissioned a study into what ground station we should get next year. We're building up a lot of our own test equipment, and we have our friends across town at the AITC at Mount Stromlo with all the facilities we would need for the flight testing. So next year is going to be a big year for MERS in that we will be refining some of these key aspects and bringing up some of the aspects which are lagging behind, like the AOCS system, and some of the more detailed design. Those will be matured a bit next year. So in conclusion, I'd like to say we've shown it can work. We can enable the microgravity. It certainly costs, and we need to look at that more and how to manage it. But it's challenging. It is challenging, but this is an opportunity. So was Rosetta. But we've got, from all this, a number of, I think, good ideas for further development, which will go beyond MERS and we can use on other missions. And so I see this as a useful vehicle for driving in R&D and furthering collaboration. Thank you.
Thank you very much, Dr. Flutter. Now, will you ensure safety during re-entry of this 27 kilogram satellite falling on property or people? I think there's a space law as well that you must ensure that you will not damage anything.
Yeah, it's an important thing, and I think I mentioned in the paper some of the regulatory things are just as difficult as technical, but there's a well-proven path to doing this, in particular in Australia, where we do allow people to re-enter things into the Woomera area, but yet it's quite a rigorous process you have to go through, and that's why I emphasized before the final re-entry we need to spend some time really characterizing the orbit so that we know exactly where we are and that we started on time so that you can predict well where it lands. And there are tools for doing that.
And ensure that your experiment will survive the crash when you land, not in water but on...
Yeah, that's something we're going to do tests on. We're going to build what the internal structure next year and do some initial tests. But this is currently a popular way of doing things now, especially where planetary protection is important. It's good if you can show you don't rely on a parachute and you can land hard.
I have two questions.
Yep.
One is who will be your potential customer, government or private company?
Anybody. I mean, the people who now put payloads on the space station, whether through nanoracks or other I mean, one of the reasons for going for the 1U cube-sized box is that we could fly nanorack payloads. So it's meant to be open to everyone.
And one more question is about the period of preparation. In case of the using business, the period of is very important for. I think the 6 months or 1 year preparation period is enough for business use, but the 1 year and 2 years period is not suitable for business application. How long will he think about your MERS mission for preparation?
I'm not sure if I understand. Do you mean preparing the design or preparing for each launch?
Preparing the design of mission.
Well, being university driven, it's not going to be extremely quick, but I think in the next, say, 3 years, there should be quite a substantial design in place. So I think it would be unrealistic to say it would be quicker.
Couple questions. One is, have you done any work to characterize what happens when you re-enter with just an increase in area as far as accuracy? My concern is that it seems difficult to hit your target without some some active control, either propulsion or changing area actively or something like that.
Well, we've followed our Japanese friends quite closely on what they did with Hayabusa, and that was a completely passive re-entry with a vehicle about the same size. So you don't need to control it. It's just the starting that is important. And then I think you can, if your stability is high, which is another thing I stress in the paper, then you can characterize that path quite well. And as long as you have a good landing area,
yeah, my concern is Hayabusa is coming hyperbolic, so it's coming at high speed. You're kind of targeting the spot, and then you have a short event. But you have this very long, slow decay that...
no, well, we have the long, slow decay initially to get us sort of primed and in position to then do a quick re-entry where the drag thing comes out further for a short period. So
do you have any thoughts on how that big drag device will look like, or?
Only a vague thought, to be honest. Something like one of those commercial ones, the Clyde-based thing, or some variant of that. The way we have the antennas actually lends itself to incorporating that into the thing. So that's another of these possible opportunities to develop.
Okay, thank you very much, Dr. Nijunik.